Hello everybody, this is Mr. Ainsworth and we're going to get into a section of this chapter dealing with how to graph a function using its first and second derivatives. Notice the title up here. Alright, so suppose that this is f prime here and this is f double prime. Okay, so we're not given the function itself, we're given the graphs of the first derivative here, this parabola right here, and the given graph of the f second double prime here of this linear function. And this kind of suggests, since we know about derivatives already, that since the second derivative is linear, the first derivative is quadratic or second degree parabola, that their original function is cubic. So I'm expecting f of x to be a cubic here. Okay, so expect f of x to be a cubic polynomial. All right, now it's not always this case. We could be dealing with trig functions, we could be dealing with many things, but in this case here, I'm expecting a cubic. And cubics behave like this right here, or like this, depending on the coefficients. Okay, so let me clear that out. So let me tell you how to interpret the graphs of the derivatives here. So let's analyze f prime first. Okay. Now, first of all, where the first derivative crosses the axes is where the first derivative equals 0, and that gives me information on its critical points. So let's say that this point right here is, let's say, 2/3 on the x-axis, and let's say that this one here, don't know exactly what it is, but let's say it's 3 1/3. Okay, I'm approximating right now. What I do know is that at this point right here, the first derivative at 2/3 is equal to 0. Okay, and that tells me that we have a critical point at 2/3. So this is a critical point. And then right here also, f prime is equal to 0 here at 3 1/3. That tells me that we have two critical points in our analysis here. So what we can do in a minute is take a look at a sign analysis on our first derivative. So let's do that. Let's go over here off to the right and let's do a little sign analysis and do a first derivative test to see where our extrema are. So since we have critical points at 2/3, we're going to graph 2/3 and the other critical point 3 1/3, just as we normally would when we do a first derivative test. Now the way you interpret the graph is like this. Let's take a look at this portion of the derivative. Okay, it's right here. And we notice that it's above the axis, so that suggests that f prime is positive. And if it's positive, that tells me that the function is increasing from negative infinity to 2/3. Okay, all these values are here above the x-axis, and so therefore they must be positive. That tells me that the function is increasing there from negative infinity to 2/3. It also is positive from 3 1/3 on to infinity over here. Okay, so that tells me that the function is increasing on two different intervals, from negative infinity to 2/3 and from 3 1/3 to infinity. I'm going to switch colors here. The portion of the derivative down here, f prime, is less than 0 because it's below the axis right here, and that tells me that it's decreasing on that interval from 2/3 to 3 1/3. Now looking at the information right here, the first derivative test tells us that we have a maximum, relative maximum at 2/3. So we have a relative max at 2/3, and we have a relative min here at 3 1/3 because it goes down and back up. And we don't know what the y values are of these min and max or this extrema here because we don't have the function itself. We can't go just substitute it back in. But we do know that the relative max occurs at 2/3 comma f at 2/3, and then the relative min occurs at 3 1/3 comma f at 3 1/3. And we're going to plot those in a minute. But before we do, let's take a look at the second derivative here, f double prime, and interpret what it means. Now at this point right here at 2, it tells me that f double prime at 2 equals 0, and that gives me information on what are called inflection points. So let's do a concavity test here and see what's going on. So 2 represents an inflection point because f double prime at 2 equals 0 because it's on the axis. All right. The portion that's below the axis down here on this dotted line right here, f double prime is less than 0, which means it's concave down from negative infinity to 2. Concave down. Why? Because it's negative. Okay, so negative implies concave down on that interval from negative infinity to positive 2. And then the portion above the axis here, right here, this dotted line in blue, the second derivative is positive, okay, greater than 0, which implies that it's concave up from 2 to infinity. Okay, and so we can use this information here to help us graph one of the many possibilities of this function. So what we do is we plot, well, first of all, we scale the axes. So let's say this is 1, 2, 3, 4, 5, 1, 2, 3, oops, 3, 4, 5, 1, 2, 3, 4, 5. You've got to scale the axes first. And we're going to plot the extrema. Okay, plot the extrema first and the inflection points. So plot extrema and inflection points, all right, first. So let's do that. I'm going to plot in red so you can see it better. So 2/3, comma, f of 2/3. Now 2/3, got to split the interval up into 3 equal parts, go 2/3 to the right, and I can either go up or down. I'm going to choose to go up here because I'm going to show only one of many possibilities for this graph. Since we don't have the function, I really don't know what the y value is, so I'm going to approximate. So let's suppose that f of, or 2/3, comma, f of 2/3 would be right here. And this is a max. So max, and it's 2/3, comma, f of 2/3. Okay, so right there. And let's suppose that the inflection point is 2, comma, f of 2. Now I don't know exactly where f2 is, but let's suppose it's 2, comma, 0. Let's suppose that that value is 0. It could be. It may not be, but it could be. Okay, so that's an inflection point at 2, comma, whoops, let me change that right here, 2, comma, f of 2. Okay, now I have to graph the relative min at 3 1/3, comma, f of 3 1/3. So I'm going to split this subinterval up into 3 equal parts, go 3 1/3 over. And since since inflection points like this one here or this one here, they're usually equidistant from the max and the min. Okay, and this is the inflection point right here. So I see that my max is way up here at 2, and my inflection point's down here on the axis. That's 2 units above the IP. I'm going to go 2 units down below. All right, and then go 3 1/3 and go down 2. Because that's how cubics behave. The inflection points are right in between the min and the max. So I'm going to call this min here. That's the minimum. And it's a minimum at 3 1/3, comma, f of 3 1/3, whatever that is. Okay, again, this is one of many possibilities, as I keep on saying. And then what I do is I use my concavity. So I'm going to switch to blue now and put my function in blue so it pops out. Now, from negative infinity to 2, it's concave down. So it suggests that my function behaves like this. Okay, so I'm going to graph it concave down. From negative infinity, all right, to 2. From 2 to infinity, it's concave up, and it's got to go through that minimum. So it suggests that the function behaves like this. It's got to go through these points. Got to go through the min, the inflection point, and my max. So my function could look like this. This is one of many possibilities. Possible f of x's, okay? Why? Because I don't know this. This is an unknown. This is unknown, and this is an unknown. So what I had to do is I said, okay, suppose it is equal to 2. You know, f of 2/3 is equal to 2. Suppose the IP is 2, comma, 0. And suppose 3 1/3 is actually, you know, negative 2. This whole thing could be shifted up or down. Keep that in mind. So it's one of many possibilities right here. Okay, and that's how the game is played, guys. Let's try it again. Okay, in a graph, this one here now, let's suppose that this is f of x here. Excuse me, not f of x, but f prime, and this is f double prime. Okay, again, if the first derivative is quadratic, which is second degree, then the original function must be a cubic. All right, so this suggests that we have another cubic, but this time the cubic is going to have a different shape. Okay, so let's take a look at f prime here and interpret the information here. Let's suppose that this point right here is 1 1/3 again, so 1 1/3, and then right here it's negative 1 1/3. Really don't know what those are, but I'm going to approximate because it looks like a third of the way. Okay, now this suggests right here, this point, that f prime at 1 1/3 is equal to 0, and that means that this is a critical point. And likewise over here, this is another critical point. Why? Because f prime is equal to 0 at this point. First derivative, whenever the first derivative is equal to 0, it gives you information on the critical points. So what we can do is graph these critical points and do a sign analysis and figure out what's going on, just like we did on the other one. So this portion down here from negative infinity to negative 1 1/3 here is all these values right here are negative, they're less than 0. And that suggests to me that it's decreasing on that interval. Likewise over here too. F prime is less than 0 because it's below the axis, and then that means the function is decreasing on that interval from 1 1/3 to infinity. Okay, the portion that's above the axis right here in blue, f prime there is positive, so it's increasing there. And this gives us information on whether we have a min or max at these points. And so I see that it's decreasing and increasing, so this is going to be a relative min. And then it goes from increasing to decreasing, so it goes up and then down, and that suggests that we have a relative max. Okay, I'll graph these in just a moment. Okay, and then secondly, we have information on the second derivative. Now the second derivative is right here, and it suggests that we have the second derivative at 0 is equal to 0 here, so we have an IP at 0. Let's do a second derivative test down here. Now, the portion above the axis here, f double prime, is positive right there. So from negative infinity to 0 is positive, which suggests that it's concave up. The portion below the axis, this portion down here, this suggests that f double prime is less than 0 because it's below the axis right here and it's concave down. From 0 to infinity, and then from negative infinity to 0 it's concave up. With that information, we can graph the function here, because this is an inflection point. So what we're going to do is we're going to graph the function. We're going to scale the axes first a little bit, like we always should do, unless it's already scaled for you. And then I'm going to approximate these values here. So what I have to do is I have to go 1 1/3 over. This is negative 1, this is 1, this is 2, 1, 2, and so on. So go 1 1/3 over, which would be right about there, and then go up or down. Okay, now it's a min. So this time I'm going to choose to go down just for funsies here. And I'm going to plot these points in red. So this is going to be my minimum here at negative, right here, sorry. At negative 1 1/3 comma f of negative 1 1/3. Right there is my minimum. Excuse me. I've got an inflection point at 0 at 0 here, and that could be anywhere I want on the y-axis here. I can put it at 0, 1, 0, 2. I can put it anywhere I want. Let's put it here just for fun right here. So I've got an inflection point here at 0, f of 0. Again, I don't know what f of 0 is because I don't have a function, guys. I just have to approximate it. Now notice I put it about 2 units above the minimum here. So my maximum has got to be somewhere over here. So I go 1 1/3 over to the right and go up about right here. And this is my max. Where? At 1 1/3 comma f of 1 1/3. Okay, and then I use my concavity. So I'm going to switch to blue now. From negative infinity here to 0, it's concave up. So it suggests that it behaves something like this. From 0 to infinity, it's concave down. So it suggests something like this. This is my function. And again, this is one of many possibilities. So one of many possible functions. Okay, remember that. I can slide this whole entire function up or down if I like. Okay, but you just have to get the proper placements left and right. for the min, the max, and the inflection point. And you have to obviously interpret the graphs properly. Okay? So you have some homework problems on this, so you have to give it a shot, but this is the basic idea. And then you're going to get a problem like this, number 3, where they don't give you graphs, they give you a table of values, and you have to interpret the information and then graph the function based upon that. Okay, so let's interpret the info first. Okay, so from negative infinity to 2, the first derivative, let's see here, the first derivative is negative, and the second derivative is the second derivative. This is the first derivative. Okay, so once more, here we go. From negative infinity to negative 2, the first derivative is negative. That means it's decreasing here. And the second derivative is negative, so it's concave down. So on this interval from negative infinity to negative 2, it's decreasing and concave down. So decreasing and concave down. At negative 2, it's undefined everywhere. That tells me that we have a vertical asymptote, okay, where x equals negative 2, of course. At negative 2 comma 0, this is an interval now. Again, you got to remember these are intervals, not points. This tells me that on that interval, since the first derivative is negative, it's decreasing, and it's positive on that interval in the second derivative, so it's concave up. So it's decreasing and concave up, decreasing, concave up, or you can just do this. On this point here, this is a point. 0, 9 halves is an actual point, and f prime of that at that point is equal to 0, which suggests that we have a critical point, because the first derivative is 0 at that point. So we have a critical point at 0, 9 halves, or 4 1/2. 0, 4 and 1/2. Add this little notation in here. I forgot to put these in the table here. On this next interval from 0 to 2, both first derivative and second derivative are positive, so it's got to be increasing and concave up. So increasing, concave up. At 2, x equals 2, it's undefined again, so we have another vertical asymptote at 2. So we have 2 vertical asymptotes, one at negative 2, one at positive 2. So I'm going to draw 2 vertical lines in a minute. And then from 2 to infinity, first derivative is positive, so it's increasing, and then negative on second derivative, so it's concave down. So it's increasing here, and then concave down. Okay, these are negative 3 and positive 3 comma 0 are points, and they're called intercepts. Intercepts, and they're x-intercepts actually, x-intercepts. So I'm going to plot those points. And then here, this information is telling me that for the entire domain, that for all values of x, for all x here, for all x, y cannot be equal to 2, which means we have a horizontal asymptote at y equals 2. So I'm going to graph that line here too. So let me scale the axes here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1. So you just got to scale them a little bit here. Okay, and let's draw the asymptotes first. We have 1 at 2. I'm just going to do this right here. So we have an x-axis here. Excuse me, a vertical asymptote here. And we have another vertical asymptote here. Let me redo that better here. You know what? It'd be easier for me just to draw it by hand. No. Yep. Sometimes it's much easier to do things by hand. Okay, so let's draw these vertical asymptotes here. 1 at 2, 1 at negative 2. So vertical asymptote, x equals 2. Vertical asymptote, x equals negative 2. We have a horizontal asymptote at 2. So y equals 2 is a horizontal asymptote here. So the function exists somewhere in between all these asymptotes. Okay, and this is where you start plotting some points. So here we go. So at 0, 4.5 right here, we have a critical point. 1, 2, 3, 4. This is 4. So right here. And let's see. So 0, 4.5. And then you got to look for concave up, concave down. So in between, excuse me. Okay, excuse me for that. I'm not feeling too well, but here we go. Okay, let's talk about in between these vertical asymptotes first. So from -2 to 0, and then from 0 to 2. So from -2 to 0, it's concave up. So it suggests that it's asymptotic to this vertical line, and it's concave up, so it has to behave like this. From 0 to 2, where is that? It's right here. It's also concave up, okay, and it suggests that function must behave like this. It's increasing and concave up, so the function is increasing and concave up. From -2 to 0, let's go back to that, the function was decreasing and concave up, so it's decreasing, it's going down, but it's still concave up. Okay, so how's it behaving on these other sides, though? Okay, so let's plot the other couple points we have. We have x-intercepts at 3, 0 here, and then at -3, 0 here. So how does it behave from 2 to infinity? Well, from 2 to infinity, it's increasing and concave down. So it's got to be increasing, no, that's increasing and concave down. Also, these are asymptotes, so it's got to get closer to these asymptotes. From -infinity to -2, you're up here, it's decreasing, concave down. So the function starts high up here, and it's decreasing, hits that point, and it's also concave down. So it's decreasing, and concave down, and because these are asymptotes, it's got to get closer to them. Okay? So you're going to have to get some experience here. You're going to have to interpret the table, what it means. Okay, what the first derivative tells you right here. This is the first derivative, and this is the second derivative. Interpret the info first, and then draw your axes, draw your asymptotes, plot your points, and use concavity and where the function's increasing and decreasing to help you draw the graph. Okay, let's just do a couple more here. Sometimes you're not given a table, you're given a set of information like this. And so what you're going to have to do is use information on the first derivative and the second derivative to help you graph the function again. And you need to graph the relative extrema, intercepts, and inflection points. So let's go ahead and give this a shot. F of 0 and f of 4 equals 0. This tells me I have a couple points. I have 0, 0 and 4, 0. These are points on the graph. Oops, 4, 0. So I can plot 0, 0 here, 4, 0 here. F of 3 equals 27. So 3, 27 is also a point on the graph. So you go right 3, up 27. It's probably right around here. So at 3, 27. What else does it tell us? That tells us, and let's do a little sign analysis down here. Yeah, for the first derivative and also second derivative. Okay, the first derivative at 3 equals 0. That tells me we have a critical point there. And if it's positive, if the first derivative, oh, let me see, critical point at 3. So let me see, critical point at 3. And right here it tells me that to the left of 3 here, the first derivative is positive. Ooh, to the left of 3. So it's positive there. That tells me that it's increasing. And the first derivative is negative to the right of 3. Well, that tells me we have a max there. Okay, so this represents a max already. It's a relative max. Okay, that's on the first derivative. Let's go to the second derivative here. Okay, now when the second derivative is equal to 0, it tells us about inflection points. So this tells me about IPs at 0 and 2, at x equals 0 and 2. So here's 0 and here's 2 on the second derivative. Okay, now we use information on the second derivative to do concavity here. So this tells me about concavity. So the second derivative is negative to the left of 0 and to the right of 2. So it's got to be concave down here and concave down here. Between 0 and 2, it's greater than 0. The second derivative is greater than 0, so it's concave up right here. And that's all there is to it. And this is an actual point right here, 2, 16, so we need to plot that as well. So right 2, up 16. Since 2, at 2, it changes concavity from up to down. This is an inflection point. And again, this is an inflection point too. At 0, 0. This is an inflection point here, IP, and then the 2, 16, which is right about here, right about there. This is also another inflection point at 2, 16. Okay, so all we have to do is just graph the function at that point, or from there. So I'm going to switch to red and start graphing the function. Okay, so it's got to be, this is a max, and using the concavity here between 0 and 2, it's concave up. So no, it's concave. That's too close. It's got to be concave up here, and then switch to concavity down here. So it's concave up between 0 and 2. From 2 to infinity, it's concave down, so it's got to hit the max and come back down, and it's got to go through this point right here. So it's concave down in this interval here, concave up here. And let me see, from 0 on, it's concave down, so it's got to switch and go concave down here from negative infinity to 0. Just look at the concavity test here. This tells you about concavity. Okay, and that's all there is to it, guys. You plot some points, plot the extrema, plot the inflection points, and go for it. Use a concavity to help you graph. Okay, use concavity to help graph. That's the key. Okay, let's try another one. Number 5 here, we've got some points here. We got negative 2, 0, 3, 0, 8, 0. So we can plot these points. So let's go ahead and do that. Negative 2, 0 is here. 3, 0 here. 8, 0 roughly here. You know what? Let's spread this out a little bit. I should have expanded the graph a little bit. I'm going to call this 1, 2. Let's see here if I can do this. 3, 4, 5, 6, 7, 8. Yeah, I'm going to do that just so I can expand it. Make it a little bit easier to see for you guys. 1, 2, 3, 4, 5. Negative 1 here, negative 2, negative 3, negative 4. Okay, so negative 1, negative 2, negative 3. This will help us see the graph a little bit. And then extend it down here, negative 2. And then down, let's go a little bit further down here, negative 3. Okay, so here we go. I'm going to regraph these points. Switch to red. So negative 2, 0 would be here. 3, 0 here. 8, 0 here. These are points. Okay, now these right here are critical points because it says the first derivative at negative 1 and at 6 is equal to 0. So these are critical points at x equals negative 1 and 6. So negative 1 and 6. Okay, so this tells me that the first derivative is positive between negative 1 and 6. Positive here. This tells me that it's negative to the left of negative 1 and to the right of 6. So decreasing here, decreasing here. Okay? That's what this information here. This tells me this is the first derivative test. First derivative test right here. And then when the second derivative is equal to 0 at 3, that tells me about an inflection point at x equals 3. Okay, next what we have is we have a second derivative test here on concavity. I know I have an inflection point at 3, so I got to test the concavity to see where it's concave up or down. Okay, so second derivative is less than 0 or negative from 3 to infinity. Okay, so it's less than 0 here, so it's negative, concave down. And then on from negative infinity to 3, it's positive, so it's concave up. Okay, so what we need to do is graph this. Let me see. So we have a point. We have 3, 0. IP at 3, 0. Look, take a look above here. 3, 0 is a point. It's an inflection point. So this is my inflection point right here. And I've got some other points here that I already know that are on the graph. And now I'm going to use my concavity here. Let me see if I plotted all my points here. Okay, so here we go. We've got a relative max at -1, comma f at -1. We don't have information on f at -1 up here, so I don't know exactly where to plot it. But I do know we have a max somewhere along this vertical line here at -1. Or excuse me, not a max, but a minimum here. So this is a minimum, and this is a max. So when I graph this here, I've got to come down here. It's got to be concave up from -3 to -infinity to 3. So concave up. So it's got to be something like this here. Concave up, where this is our minimum here at -1, comma f of -1, whatever that is. Because again, this is a relative min and this is a relative max. And then at 6, it's got to hit a high point somewhere up here, and then it's got to come back down. Why? Because it's concave down here. It's concave down from 3 to infinity. So concave down here, concave up here, with a minimum down here at -1, comma f at -1, and then a max at 6, comma f of 6. Okay? So using concavity, I know it's got to be behaving something like this to the left of 3, and then concave down to the right of 3, looking at your concavity. And that, my friends, is example 5. All right. I'm going to end the video here, and you try your homework, and I will get back to you in class and check your understanding and also help you out if you need some. So do your best, check your homework, check online on the solutions, and I'll see you tomorrow.